In this video, we're going to talk about how to find the domain of a function using an algebraic method. Are you ready? In some questions, we come across expressions like this, where it says f such that x arrow to x plus 3. Well, that is okay. This just means f such that, the colon stands for such that, every input, if x represents the input, every input becomes 2 times the input plus 3. Well, that's all right. But what about this comma x greater than or equal to 0? Sometimes, some students get a little perturbed by that and they think, is it part of the question? In a sense, yes, it is part of the question, but it is just saying that this is your domain. This is your domain, because if I call this x as the input, and remember we said input is the domain, it's actually restricting the domain or the input values to only non-negative values. X greater than or equal to 0 means x should be non-negative. So in this case, it is given in the question that f of x is 2x plus 3 and the domain is all non-negative. However, there will be other questions where the domain is not specified like this, and we have to take a look at the definition of the function given in the algebraic form and then use some of our algebraic knowledge to determine what is the domain of the given function. The algebraic method to find the domain of a function is sort of indirect. I'll explain what that means. Instead of answering the question as to what is the domain of the function, meaning what is allowed, what kind of values of x are allowed in the input, we answer the same question by looking at it another way, by finding out what values are not allowed. Make sense? Let's take an example, shall we? What I've done is that I divided into 3 sections. There are 3 cases as we understand how to find the domain of a function algebraically. Okay? The first case is involving fractions. Now we all know that in numbers, when you have a numerator divided by a denominator, we are always told, watch out, the denominator cannot be 0. You cannot divide by 0. Sort of use the same idea when there is a function. So if you have a term in x in the denominator, we just say that whatever the term is in the denominator, that must not be 0. So we say in this case, if y is equal to 1 over x, we say, oh, there's an x in the denominator. This means that x must not be 0. X cannot take the value 0. And this sort of puts a restriction to the values of x that are allowed as input. So if x cannot be equal to 0, the domain would be x belongs to negative infinity, 0, union, 0, infinity. Now that is in the interval notation because the question asked for the domain in the interval notation. This clearly means that there's every real number but 0. Every real number before 0 is allowed, every real number after 0 is allowed in the domain, but 0 is the only one that is restricted or kept away. And how did we answer this question? We answered this question using the indirect approach. Which value is not allowed? Understand? Let's look at the other example. Again, there's a fraction. What's the term in the fraction this time? It's 3x plus 9. So we say that the term in the denominator must not be equal to 0. 3x plus 9 cannot be 0. If fx is equal to 8 over 3x plus 9, then the denominator, which is 3x plus 9, cannot be equal to 0. And when we solve this inequation, we'll get 3x cannot be equal to negative 9, or x cannot be equal to negative 3. X cannot be equal to negative 3. That is the indirect approach. What's the value of x that is not allowed? In this case, it's one value. It could also be more than one value, by the way. So in order to answer the question, what is the domain of this function, 8 over 3x plus 9, we have used an indirect approach, and we are saying that the domain is all real numbers except x is equal to negative 3. So in the interval notation, we can write it as x belongs to negative infinity, comma, negative 3, union, negative 3, infinity, and that is the domain in the interval notation. Again, it means that every real number except for negative 3 is included in the domain of this particular function. One more example of one fractions. Look at this. This time the denominator is a quadratic expression. So in order to answer the question, when is the denominator going to be 0, we have to say, okay, when does x squared plus 7x plus 12 is equal to 0? Now that would mean, let me just bring this into the view of the camera, we need to try and figure out the solution to this quadratic equation. When is that becoming equal to 0? A quick factoring would tell me that this is x plus 4, x plus 3, and the two values of x that make that quadratic equation 0 is x equals -4 and x is equal to -3. Those are the values of x. X is equal to -4 and x is equal to -3, where the denominator of this function, y is equal to 6x over x squared plus 7x plus 12. Those are the values of x where the denominator is going to become equal to 0. So that means x equals -4 and x equals -3 is not allowed in the domain of this function. How do we write it in interval notation? Here we go. I write the domain is all x values in the interval -infinity all the way up to -4, but then union, watch out, I'm going to write in the next line, -4, -3, union -3, infinity. What this means is that, you know what, -4 is not allowed and -3 is not allowed, but every real number in between -4 and -3 is included or allowed in the domain. Okay? This is case 1, the case where we have fractions, and we know that in a fraction, the denominator cannot be 0. The second case is that of radicals. A radical is just like a square root. Okay, the square root sign is sometimes referred to as a radical, and we know that the term inside that radical sign, the term inside here is x minus 3. Okay, the term inside the radical sign, which means x minus 3, has to be greater than or equal to 0. Non-negative, which means x minus 3 is greater than or equal to 0. And when we solve that inequality, we'll get x greater than or equal to 3. That is the restriction for the domain of a function that is defined by y is equal to the square root of x minus 3. So that in interval notation, we would write the domain as x belongs to the interval, left end is closed where 3 is allowed, and the right end is open at infinity. The second example is when the function is defined as the square root of term inside the radical is x squared minus 9. So we set that term x squared minus 9 as non-negative, which means greater than or equal to 0. And then when we solve that inequality, we'd get x squared must be greater than or equal to 9, which upon further simplification should give us x must be greater than or equal to 3, or x must be less than or equal to a minus 3. So these are the set of permissible values for a function defined by square root of x squared minus 9, and the domain, when you write it in interval notation, can be written as x belongs to -infinity, -3, closed at that end, and then union 3, infinity. Next example, this is f of x is equal to the square root of 4 minus x squared. Again, we look at the term inside the radical. The term this time is 4 minus x squared inside the radical. So we say 4 minus x squared. The entire term must be non-negative. So when we solve the inequality, 4 is greater than or equal to x squared. And when we solve it further, this is the same thing as x squared is less than or equal to 4, which would give us the values of x are less than or equal to 2 and greater than or equal to -2. This is the set of all permissible values of x for a function defined as under root of 4 minus x squared. So that the domain, when you write the domain in interval notation, would be domain x belongs to the closed interval, because both endpoints are now included, -2, 2. There you go. So what did we do so far? We saw that in order to answer the question of what is the domain, instead of answering directly what kind of values of x are allowed, we used an indirect approach. We said, okay, what value of x is not allowed? In the first case, we saw fractions, and you know that in a fraction, the denominator cannot be 0. So we try and find out what values will make the denominator 0 and exclude those values. Do not allow those values into the domain. In the same way, the second case we saw was about radicals, meaning the square root, and we said that the entire term inside the square root must be set as non-negative. That means in this case it was x minus 3, not just x minus 3, the entire term inside the radical. Like in this case, it would have been x squared minus 9. And after you solve that inequality, x squared minus 9 greater than or equal to 0, the values you get would be the permissible values, a set of permissible values that are allowed in the domain. The third case, the final case, is a combination of the fraction and the radical. Let me just show that to you. The third case is a combination of the radical and the fraction. So we combine those conditions. In a fraction, the denominator cannot be 0. In a radical, the term inside the radical sign must be greater than or equal to 0. How do we combine? Let's take a look at this example. F of x is defined in this case as 5 over the square root of 2x minus 10. Now we know that the denominator cannot be equal to 0. And we know that the term inside the square root, in this case, the term is 2x minus 10. So we know that 2x minus 10, typically we would have written it as greater than or equal to 0. Is that right? But because that term is in the denominator, this time we say it has to be just greater than 0. Just greater, strictly greater than 0. 2x minus 10 is greater than 0. And then we solve the inequality and we continue as before. So you get 2x must be greater than 10 or x must be greater than 5. And that is the restriction for the domain for this function. That means you can write the domain as x will only be the values 5 infinity, okay, which means 5 is not included, but everything greater than 5 is included. Let's take a look at the other example, okay. Again, you have f of x is equal to 11 over the square root of x squared minus 100. Again, we say the term inside the square root, and this time the square root is in the denominator, so we write x squared minus 100 greater than 0. Only greater than 0, not greater than or equal to 0, okay, because it's in the denominator. So when we solve that inequality, you'll get x squared is greater than 100. Solving that inequality further, you should get x must be greater than 10 or x must be less than a negative 10. And then when we write that in interval notation, you'll write it as the domain is x belongs to negative infinity, negative 10, union 10, comma infinity. One more example, last example. Under root of x squared minus 25 divided by 3x minus 24. This time the radical is in the numerator. So we can say x squared minus 25 can be greater than or equal to 0. Can you see that? Because it's in the numerator this time. But the denominator has something else. We can say 3x minus 24 should not be equal to 0. Okay, that's the combination idea. So the denominator is 3x minus 24 and the numerator is that square root of x squared minus 25. So let's solve them separately. X squared minus 25 greater than or equal to 0 must give us x squared is greater than or equal to 25, which when you solve it further would give you x must be greater than or equal to 5 or x must be less than or equal to a negative 5. On the other hand, when we try and solve 3x minus 24 is not equal to 0, we should get 3x is not equal to 24, which means x must not be equal to an 8. Okay, so those are the three conditions that we have. You've got x cannot be equal to 8, x must be greater than or equal to 5, x must be less than or equal to negative 5. These are the permissible values for the domain for this function defined as the square root of x squared minus 25 over 3x minus 24. And the way we write it in interval notation is x belongs to the interval negative infinity to negative 5, closed at negative 5 because 5 is included, union 5, comma 8, open at 8 because 8 is not included, union, again open at 8, and all the way up till infinity, and it's open there. Today, we saw an algebraic way of how to find the domain of a function. If you know of any other way to find the domain of a function algebraically, please mention that in the comments below. I'd love to hear from you. Thank you so much. I'll see you in the next video.